Welcome to this coding walkthrough. Today, we'll explore problem number 738, titled Monotone Increasing Digits. We'll break it down step by step, starting with a brute force approach and working towards an optimal solution. Let's dive in and build a clear understanding of the problem and its solution. The problem we are solving is called monotone increasing digits. The goal here is to take a non-negative integer, n, and return the largest number that is less than or equal to n where the digits are in monotone increasing order. Now, what does monotone increasing order mean? It simply means that for every pair of adjacent digits in the number, the left digit must be less than or equal to the right digit. For example, in the number 123, we see that 1 is less than or equal to 2, and 2 is less than or equal to 3, so this number satisfies the condition. However, in the number 321, the digits are not monotone increasing because 3 is greater than 2. The input to this problem is a single integer n where n can range from 0 up to 1 billion, and the output is the largest number that meets the monotone increasing condition. This ensures that we are working with valid integers in a well-defined range. Let's look at the first example to understand this problem better. If the input n is 10, we want to find the largest number less than or equal to 10 where the digits are in monotone increasing order. The output in this case is 9. Why? Because 10 does not satisfy the condition, the first digit, 1, is greater than the second digit, 0, which breaks the monotone increasing rule. The closest valid number below 10 is 9, which is a single-digit number and inherently satisfies the property. Now consider the second example, where the input n is 1234. Here, the digits are already in increasing order, as 1 is less than 2, 2 is less than 3, and 3 is less than 4. Since the input itself meets the condition, the output is simply 1234. For the third example, the input n is 332. This number does not meet the monotone increasing condition because the first digit 3 is equal to the second digit, but the second digit 3 is greater than the third digit 2. To fix this and find the largest valid number, we reduce the leftmost 3 to 2, which makes it smaller, and then set all digits to the right of it to 9. So, the result becomes 299. This ensures that the new number is the largest possible while still satisfying monotone increasing digits. The key takeaway here is that when a digit violates the condition, adjustments may need to cascade to the left, and all subsequent digits need to be maximized to 9 to get the largest valid result. Now let's review some edge cases. First, for single-digit numbers, any input n between 0 and 9 is inherently monotone increasing, so the output is simply n itself. For example, if n is 5, the output is also 5. Next, for very large numbers, such as those close to the upper limit of 1 billion, the algorithm should still handle these efficiently. For instance, if n is 987654321, the output would be 899999999 after making the necessary adjustments. Lastly, consider cases where a single-digit adjustment cascades to higher places. For example, if n is 120, the second digit 2 needs to be reduced to 1, and the last digit is set to 9, resulting in 119. These edge cases emphasize the importance of handling different scenarios carefully to ensure the solution is both correct and efficient. To begin exploring our options, let's consider the brute force approach. The intuition here is straightforward. We start with the given number, n, and systematically generate all numbers less than or equal to n. For each of these candidates, we check if their digits are in a monotone increasing order. Once we find the largest valid number that meets this condition, we return it. The steps are simple: generate all numbers from n down to 0, then verify each one to see if its digits are in a non-decreasing sequence. While this method is easy to implement, it comes with significant trade-offs. The time complexity is O, n*d, where n is the input number and d represents the number of digits in each candidate. This is because we're iterating through all numbers and performing repeated digit checks. Additionally, the space complexity is O, d, as we only store digits for each number under consideration. While simplicity is an advantage of this approach, the inefficiency becomes a major drawback, especially for large values of n, since we're performing redundant checks and iterating through numbers unnecessarily. Now, let's shift focus to the more efficient greedy approach, which centers on direct digit manipulation. Instead of generating all possible candidates, we analyze the digits of n to fix any violations of the monotone increasing property. The key observation here is that a number is monotone increasing only if all adjacent digits satisfy the condition d_i equals d_i plus 1. If we find a digit where d_i plus 1, the number becomes invalid. To address this, we reduce the problematic digit d_i by 1 and set all digits to its right to 9. This ensures that the number remains as large as possible while satisfying the monotone condition. The process involves converting n into a list of digits, traversing the list from left to right, and greedily correcting any violations. After making adjustments, we replace all digits to the right of the adjusted position with 9. Finally, we convert the list of digits back into a number and return the result. This approach drastically reduces the time complexity to O(d), where d is the number of digits in n. The space complexity remains O(d), as we still store the digit list. While efficient, this method requires careful implementation to avoid off-by-one errors when adjusting digits, underscoring the need for precision in handling edge cases. Ultimately, we select the greedy approach as our chosen strategy due to its clear efficiency advantages over the brute force method. By directly manipulating the digits of n, we simplify the problem from exponential complexity to linear complexity with respect to the number of digits. The core insight lies in fixing violations incrementally without needing to backtrack, making the solution both elegant and optimal. Compared to brute force, the greedy approach is far superior for large inputs, as it avoids the computational overhead of iterating through all possible candidates. While the implementation does demand a careful handling of edge cases, such as numbers like 1000 or 332, the trade-offs are minimal compared to the significant performance benefits. In conclusion, the greedy strategy strikes the perfect balance between efficiency and correctness, making it the ideal choice for solving the monotone increasing digits problem effectively. The problem we are tackling here is to find the largest number less than or equal to a given positive integer, n, such that its digits are in monotone increasing order. This means that each digit in the number must be greater than or equal to the digit before it. For example, the number 123 has monotone increasing digits, but 321 does not because 2 is less than 3. To solve this problem, we start with a basic brute force approach. The intuition behind this method is straightforward. We begin with the number n and repeatedly check if it satisfies the monotone increasing condition. If it doesn't, we decrement the number by 1 and check again. By doing this, we ensure that we will eventually reach the largest valid number. To implement this, we initialize the process with the given number n and define a helper function, is monotone increasing, which will help us verify if a number satisfies the monotone increasing condition. This sets the foundation for our brute force solution. The helper function is monotone increasing is central to this approach. To define it, we first convert the number x to a string so that we can easily access and compare its digits. Then, we iterate through the digits in order, comparing each digit with the one before it. If we find any digit that is smaller than the previous one, we immediately return false, as this violates the monotone increasing property. On the other hand, if the loop completes without encountering any violations, we return true, confirming that the number satisfies the condition. With this helper function in place, the next step is to iteratively check numbers. Starting from n, we decrement the number by 1 in each iteration and use the helper function to check if the current number is monotone increasing. As soon as we find a number that passes the check, we exit the loop and return it as the result. This ensures that we get the largest possible number satisfying the condition. The brute force approach, while simple, guarantees correctness because it exhaustively checks each number from n downward until it finds the solution. This makes it a reliable method, albeit inefficient for large numbers. The simplicity lies in the fact that we are directly checking each number, and the helper function ensures the correctness of our monotone increasing condition. Speaking of efficiency, the helper function processes the digits of a number in a time proportional to the number of digits, which gives it a complexity of O log n. However, in the worst case, the algorithm may need to decrement all the way from n to 0, performing these checks for each number. This results in an overall time complexity of O n asterisk log n. While this is not ideal for large numbers, it highlights the importance of exploring optimization techniques. For instance, rather than decrementing one by one, we might modify the digits of n directly to make them monotone increasing, which we will explore in optimized solutions. The data structures used in the brute force approach are straightforward. Converting the number to a string is key, as it allows us to easily access and compare adjacent digits. This simplifies the process of checking for monotonicity, but it does introduce some overhead due to the conversion process. When it comes to edge cases, there are several scenarios to consider. Single-digit numbers, such as 5 or 9, are always monotone increasing, so the algorithm will simply return the input in such cases. For numbers that are already monotone increasing, such as 123 or 111, the helper function will confirm this immediately without requiring any modifications. Another interesting case involves numbers like 120. When decrement, it becomes 119, which is also not monotone increasing. The algorithm will continue decrementing until it finds a valid number, such as 111. These examples demonstrate how the algorithm handles different kinds of inputs and edge transitions. To better understand the brute force approach, let's walk through an example where n equals 321. We start by checking if 321 is monotone increasing. Converting it to a string gives 321, and comparing the digits reveals that 3 is greater than 2, which violates the condition. Therefore, we return false and decrement n to 320. The process repeats, checking 319, 318, and so on. Eventually, we reach 299, where the helper function confirms monotone increasing digits. Specifically, the digits 2, 9, and 9 satisfy the condition, as each digit is greater than or equal to the one before it. At this point, the function returns true, and the algorithm outputs 299 as the result. This example highlights how the brute force method systematically works its way down from n to find the largest number that satisfies the monotone increasing property. Analyzing the complexity of the brute force approach, we find that its time complexity is n*log n. This is because, in the worst case, we decrement from n all the way to 0, and for each number, we perform log n comparisons to check its digits. The space complexity is log n, as we need to store the string representation of the number during these checks. While this approach is computationally expensive for large inputs, it has the advantage of being easy to implement and guarantees correctness. However, its inefficiency highlights the need for optimization. By manipulating the digits of n directly, we can reduce the number of iterations and achieve significant performance gains. Ultimately, the brute force approach serves as a valuable starting point for understanding the problem, but more efficient techniques are necessary for handling larger inputs effectively. This code solves the LeetCode problem monotone increasing digits using a greedy approach. First, we convert the input number n into a list of its digits. The key idea is to traverse the digits from right to left to detect places where the monotone increasing property is violated. If we find such a violation, we adjust the left digit, making it smaller by 1, and mark the position where this adjustment occurred. The next step is to set all digits to the right of the marked position to 9. This ensures that the resulting number is the largest possible monotone increasing number less than or equal to n. Finally, we convert the adjusted list of digits back to an integer and return it. This approach is efficient because it processes each digit at most twice, once during the traversal and once when setting values to 9. The time complexity is d, where d is the number of digits in n, and the space complexity is d, due to the list of digits. This makes the solution both optimal and easy to understand. This is the Java implementation of LeetCode problem number 738, monotone increasing digits. The logic mirrors the Python implementation, with adjustments for Java-specific syntax and type declarations. The solution uses a character array to manipulate the digits, ensuring monotonicity by traversing the array from right to left. Any digits to the right of the adjusted position are set to 9. Key differences include Java's char handling compared to Python's list of strings, and the explicit conversion between strings and integers. Let's start with the example where n equals 1234. First, we initialize by converting the number into a list of its digits, so we get 1, 2, 3, 4. We also set a variable called marker to the length of this list, which is 4. This marker will help us identify where changes need to happen if the digits are not monotone increasing. Next, we traverse the digits from right to left, starting at index 3. At index 3, we compare 4 with 3. Since 4 is greater than or equal to 3, we do nothing and move on. At index 2, we compare 3 with 2. Again, 3 is greater than or equal to 2, so no changes are needed. Finally, at index 1, we compare 2 with 1. Since 2 is greater than or equal to 1, we continue without making any changes. Now that there are no violations, the marker remains unchanged at 4. This means no digits need adjustment. The result is simply converting the list back into the integer 1234, which is our output. Now let's consider the example where n equals 332. We begin by initializing the process. First, we convert the number into a list of digits, giving us 332. Then, we set the marker to the length of the list, which is 3. Starting our right-to-left traversal at index 2, we compare 2 with 3. Since 2 is less than 3, we decrement the digit at index 1 by 1, turning it into 2, and update the marker to 2. The digits now look like 3, 2, 2. Continuing to index 1, we compare 2 with 3. Again, 2 is less than 3, so we decrement the digit at index 0 by 1, making it 2, and update the marker to 1. The digits are now 2, 2, 2. At this point, the traversal is complete, and the marker indicates where adjustments are necessary. After determining the marker position, we proceed to modify the digits. Starting from the marker, which is at index 1, we set all digits from this point to the end of the list to 9. This gives us the updated list, 299. Finally, we convert the list of digits back into an integer, resulting in 299. This is the largest monotone increasing number less than or equal to the original input of 332. Now, moving on to the next example, we have n equal to 1000. As with the previous examples, we begin by converting the number into a list of digits, which gives us 1000. We also initialize the marker to the length of the list, which is 4. In this case, we traverse the digits from right to left, starting at index 3. At index 3, we compare 0 with 0. Since 0 is greater than or equal to 0, no changes are made. At index 2, we again compare 0 with 0, and similarly, no changes are needed. At index 1, we compare 0 with 1. Here, 0 is less than 1, so we decrement the digit at index 0 by 1, resulting in 0, and update the marker to 1. The digits now become 0, 0, 0, 0. After identifying the marker, we modify all digits from index 1 to the end of the list, setting them to 9. This gives us 0, 9, 9, 9. Once converted back into an integer, the result is 999, which is the largest monotone increasing number less than or equal to 1000. This concludes the solution walkthrough, illustrating how we handle different cases to achieve the desired monotone property. The time complexity of the algorithm can be broken down into several key steps. First, we convert the integer n into a list of its digits. This process involves converting n into a string and then into a list, which takes time proportional to the number of digits in n, or OD. Next, we traverse this list of digits in the first loop, starting from the second to last digit and going back to the first. This loop runs 4 D1 iterations, and during each iteration, we perform comparisons and potentially modify a digit. Since these operations are constant time, the overall complexity of this loop is OD. After determining which digits need adjustment, we have a second loop that updates all digits to the right of the marker to 9. This loop also runs at most D times, and each iteration involves an O1 operation. Combining all these steps, the time complexity of the algorithm is OD, 1 pass to convert the number, 1 pass to identify adjustments, and 1 final pass to update the digits. This makes the algorithm highly efficient, with its runtime directly proportional to the number of digits in the input integer. Now let's look at the space complexity. The algorithm uses a list called digits to store the individual digits of the input number n. The size of this list is proportional to the number of digits in n, making it OD. Apart from this list, the algorithm uses a few integer variables like marker and I, which require constant space, or O1. Since there are no recursive calls, additional data structures, or auxiliary space requirements beyond the digits list, the space complexity of the algorithm is dominated by the storage of this list. Therefore, the overall space complexity is O(D). This means the algorithm is space efficient, as it only requires memory proportional to the number of digits in the input. To understand the efficiency of this approach, let's compare it to a naive or brute force solution. A naive method might involve iterating through all numbers from n down to 0 and checking if each number satisfies the monotone increasing property. For each number, we would convert it to a string and compare adjacent digits to verify the property. This would result in a nested loop, where the outer loop runs up to n times, and the inner loop performs up to O(D) operations for each number, making the total time complexity O(n*(D***). In contrast, the optimized approach directly modifies the digits of n without iterating through all numbers. By traversing the digits only twice, once to identify adjustments and once to finalize the digits, the algorithm achieves a time complexity of O(D). This is a significant improvement over the brute force method, particularly for large inputs, as the optimized approach scales linearly with respect to the number of digits in n. We can also analyze the algorithm's performance in different scenarios. In the best case, if the digits of n are already monotone increasing, the first loop will traverse the digits without making any changes, and the second loop will not execute. This results in a time complexity of O(D). In the worst case, where all digits require adjustment, such as when n is 987,654, the first loop updates multiple digits, and the second loop replaces all digits after the marker with 9. Even in this case, the time complexity remains O(D), as each digit is processed a fixed number of times. On average, some digits may need adjustment while others do not, but the overall time complexity still remains O(D) due to the linear traversal. Mathematically, the algorithm iterates over the digits at most twice, and each operation within these loops is constant time, making the total operations proportional to the number of digits, d. Since d is logarithmic with respect to n, specifically, d equals log 10 n, the time complexity can also be expressed as O log 10 n. However, for clarity, we use O(D) to directly relate it to the number of digits. The space complexity, as discussed earlier, is entirely determined by the digits list, which is also O(D). This balance of efficiency in both time and space makes the algorithm well suited for this problem. When solving the monotone increasing digits problem, there are several common mistakes to watch out for. First, it's important to account for edge cases like single-digit inputs. A number less than 10 is inherently monotone increasing, so your solution should handle these without performing unnecessary calculations. Next, a critical error arises when failing to properly backtrack after encountering a decreasing digit. If you simply reduce the troublesome digit without setting all the following digits to 9, the result will be incorrect. For instance, with the number 332, decreasing the first 3 to 2 and leaving the rest untouched produces 322, which isn't monotone increasing. The correct adjustment here would be to make it 299. Another pitfall involves over-relying on string conversions for digit manipulation. While converting numbers to strings can simplify some operations, it can become inefficient for larger inputs. It's better to work directly on digits when possible. Finally, the brute force approach, generating all numbers up to n and checking each one, might seem straightforward but is highly inefficient for large values of n, like 10 to the power of 8. This can lead to performance issues, especially in competitive programming scenarios, so it's crucial to adopt a more optimized solution strategy. Off-by-one errors in digit comparisons are another frequent source of bugs. When iterating through the digits of a number, ensure that each pair of digits is compared correctly without skipping or overlapping. For example, in the number 1234, you need to verify that 1 is less than or equal to 2, 2 is less than or equal to 3, and 3 is less than or equal to 4. Misaligning these comparisons can lead to incorrect results. Now, from an interview perspective, it's essential to understand the constraints of the problem. Brute force methods are inefficient, so you should focus on optimizations that reduce the solution's time complexity. Leveraging the monotonicity property is key. Once you identify a decreasing digit, adjusting it and setting all subsequent digits to 9 is often sufficient to achieve the desired result. Optimizing how you manipulate digits is another important consideration. Working directly with integers can reduce the overhead associated with string operations. Lastly, when discussing your solution, be ready to explain the trade-offs between different approaches. For instance, the brute force method is simpler but inefficient, while a greedy or backtracking approach offers better performance depending on the context. This demonstrates not only your technical ability but also your strategic thinking. This problem is closely related to several others that you might encounter in coding interviews. Of course, the primary problem here is LeetCode 738, monotone increasing digits, which we've been focusing on. Another related problem is LeetCode 402, remove k digits. In this problem, the goal is to construct the smallest monotone number by selectively removing digits, which also involves strategic digit manipulation and optimization. Then there's LeetCode 316, remove duplicate letters, which requires maintaining lexicographical order while removing duplicates, another scenario where careful digit or character level adjustments are critical. Finally, LeetCode 121, best time to buy and sell stock, may seem unrelated at first glance, but it shares a similar greedy strategy. Both problems involve identifying key points where decisions need to be made to optimize the outcome, which is a valuable skill across a variety of algorithmic challenges. There are several approaches you can take to solve monotone increasing digits, each with its own trade-offs. The brute force method involves generating all numbers up to n and checking each one for monotonicity. While this approach is straightforward, its time complexity is O, n*d, where d is the number of digits in n, making it highly inefficient for large inputs. A much better option is the greedy approach, which is considered optimal. Here, you traverse the digits of n, identify the first decreasing digit, reduce it by 1, and set all subsequent digits to 9. This approach achieves a time complexity of O(d), which is significantly faster. Backtracking is another possible method. It explores all ways to adjust the digits to ensure monotonicity, offering more flexibility but at the cost of exponential time complexity in the worst case. Finally, there's the dynamic programming approach, which involves storing intermediate results for subproblems, like the largest monotone number formed with the first k digits. While this can sometimes reduce computation, it often introduces unnecessary complexity for this specific problem, as the greedy approach already provides an efficient solution. Understanding when to use each of these methods is key to mastering this type of problem. Great work! To summarize, we tackled problem number 738 by exploring various approaches, from brute force to optimization. We discussed key concepts, complexities, and how to apply these ideas to similar challenges. Keep practicing, and don't forget to like and subscribe for more helpful content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!